I hope you guys can hear me.
We can hear you.
Yeah, we
Daniela,
can hear you.
We can.
hello.
I can hear you.
Is anyone hearing me?
Hello, I can hear you. Yes, yes.
Yeah,
All
we
right,
can hear you. We can hear you.
Can you hear
all
us?
right. Yeah, so control. Okay. So, in case I'm making any mistakes, you guys are free to correct me. Let's not assume that I know it all. All right. So, um, for control, we all know that it's like a minimization, maximization problem, and all. So that's basically the concept. Trying to get either minimum fuel or minimum distance or minimum energy. Right. Can you guys still hear me?
Yes.
Yes.
All right. So first, it started with talking about dynamics of a function. Previous control we did in year three. We first had to like model the system. Then we'll get the dynamics. Let me see if I can write. How do I annotate again? Draw. Can you see what I wrote?
Yeah, but it's a bit
Yes.
faint.
All right. All right. So for dynamics of a system, mm, wait, was there a site that you? I think there was a site that you used to write, like a site that has a whiteboard or something.
Yes, there is.
Any other?
Hold on, let me send it to you.
All right.
I see it's on Ubuntu. Then can you hear me, Bernard?
Yeah, I'm hearing.
I say I see it's on Ubuntu.
Yeah,
Okay, because I'm
still a
seeing
bunch.
Firefox
I have
too.
Windows too.
Yeah.
Um, now me, now me.
Hold on, I'm sending it to you.
All right.
I've sent it. Check your WhatsApp.
You sent it on WhatsApp.
Yeah.
All right. Did you send it to the group chat? Now me. Did
You
you
don't
send
have
it
to
to the group chat?
reload. 'Cause I sent it to you. Very soon.
I'm not hearing you.
I don't think it has loaded on your WhatsApp.
Your phone is not connected or something. Check your phone.
It's not on my phone either. Okay, it just came in. All right.
Please remove the SSD. Thank you, Ashley.
Sorry, that's where I save my contacts. All right. All right. So for the beginning of the note chart, um, there are types of regulator. So we're given two types of regulator basically. The first one is close to the one that we normally work with, like from previous year theory. That's the linear regulator. So for this linear, um, I guess we are familiar with this system dynamics. A x. So now this v here is like a constant. This a, let me check for the actual definitions. Or does anyone still remember them?
Not
Can
me.
you guys still hear me?
Yeah, I can hear you.
Yeah. The meaning of A. I know A is a matrix. That's a 3 by 3 matrix. Then B is a 2 by 2 matrix. And so it's just a column matrix. But they have like meanings. Okay, hopefully I'll check that out before end of show. So this is what models the linear regulator. It's actually just a linear equation. Then the second one is the model reference adaptive control. So that's the two that we're working with. So later on, that's when we'll be like working more with them. But for the first class of for the first part of the class we didn't like touch anything relating to this. We're just looking at functions, minimizing them and maximizing them. So there was one that we did. So before we solve that example actually, let's talk about local minimum and local maximum. How do I wipe this board now?
You can undo or erase,
Okay, undo.
like Control Z.
This erasing is slow, but alright. Alright, so for a graph of something like this, let's say we have a graph like this, for instance, and then we can give here maybe A, then can give here B, and let's say here C. Alright, so when we're talking about local minimum and local maximum, relative minimum, relative maximum. So for if you are taking a range, for instance, between A and B, you are considering just the range between A and B. The highest minimum, minimum is usually something that curves down like this, and maximum is one that curves up like this. The peak point is the maximum point, the least point is the minimum. So if you are taking between this range, the highest minimum is your absolute or your local minimum. The reason why it's local is because you're actually looking between this range, but there's a possibility that this is not the only range that the graph contains. As you can see, the graph is actually wider than this, but we're just looking between here and here. So that's why it's local or absolute minimum. Now, this one here, can I change the color of this pen? Okay, can't change the color. All right, you can see this where I am
There's a
here.
palette there.
There's a palette. Okay, I've seen it. All right. So now, for this point here, where I put the red this in, this is this is a relative minimum, because if you look between this red and this blue, this one is actually more. So the highest minimum is your local minimum. Why this one is the relative? No, I'm mixing it up. All right. Sorry. If you are looking between here and here, this is a local minimum. This is between a certain range. The highest minimum is your local minimum, but this is your relative. Yeah, relative minimum. Then talking about the maximum, this one is the absolute maximum, the highest. So that's absolute, and this is the relative. Is lower than this other one. Right.
Sorry. What about the one in the middle?
This one
Yes.
is also a relative maximum. It's a maximum, as you can see, just like this curve, but it's not the highest. If you're looking at this whole range, it's not the highest. This is the highest. So this is the absolute. So this is a relative. This is a relative when you're looking at the whole range. But if you're just taking a like maybe just this range, then this will be the absolute maximum if it's just this range. But if you're looking at the whole range, the highest one is the absolute, then these ones are just relatives. I think you get
Okay.
it.
Yeah.
All
So
right.
like let's say we are just looking at that range. There won't
Mm.
be relative maximum.
Yes, there won't be relative maximum, just absolute maximum. That's the only one that it contains, just this range. You
Sorry,
get
Bernard. Bernard, is there a
yeah.
difference between absolute and local?
No, absolute is like another word for local.
Okay, all right. All right,
The
thanks.
idea, the reason why it is called local is because you can be looking at it in a range. Like I said, now if you're looking at it in only this range, it's absolute or local. The reason for the
All
local
right.
is as a result of the range.
All right. All right, thank you.
Right. So how do I wipe this board again without the eraser? Okay, undo. There should be an easier way.
You can use Control Z this way or something.
All right. So now for a function of this sort, let's say um eraser. So now a function that contains, you can say x1 and x2, for instance, x1 comma x2. We have a function. I can just give any function though, but it's not necessarily this, maybe plus y squared. Only we can see it, x squared plus y squared. Can we see it?
Yes.
All right. So now, for us to find out if this function is a minimum or a maximum, we have to find the second derivative. So the second derivative of the function tells us the type of critical point it is, while the first derivative tells us um, the first derivative, we equate it to zero, and then we'll find out what point, maybe on the x, on the y plane, that the critical point is at. For instance, you can have a graph like this. Let's assume this is z-axis, for instance, x, and this is y. So we can have a graph, like a 3D graph. Let's just try to like picture it. A 3D graph of this sort. I believe we understand what I'm talking about, like a 3D graph. Here will be the maximum. Do you get? Yes. So now this function here is actually the z part of the graph. Okay, I didn't even draw the graph on. Let me erase the graph. Let me erase the graph first. It's supposed to be xy plane is supposed to be like on the so who's talking? So this is the y. This is the y, and then this is the z. So now that same graph I drew, something like this. So here is the maximum. So how we know what type of graph it is, if it actually curves up like this, or if it curves down, is by finding the second derivative, x squared. And we also find this. We can see this, right? So can we see
Yes.
this? All right.
Yes.
So now, if this one and this one also, if the value we get for them after differentiating it, if we get a positive value, then it's a minimum. But if we get a negative value, it's maximum. You get. So if you get a negative value maximum, it means the graph is going to be something like this graph that I drew over here. You get the idea?
Yeah.
Okay. So let's solve the question that we have here. All right. So I'm giving theta to be equals to 1 over 1 minus x squared x1 squared plus this. Then a plus 1. All right. So the first thing we have to do is to find our d theta over dx1. And the rule says there are two things that the differentials will tell us. The first differential, the first derivative rather, will tell us what point on the x1 or on the x2 plane that the maximum is on. It will tell us at what point on the x1. And then this one, this is equal to 0. That's what the condition says. And then for this one, the theta x2 will be equal to 0 also. So when we solve this, we can use to find what point x1 that the maximum is on or the minimum, because we don't know what it is yet until we find the second derivative. Then this other one, can you see my cursor? Um, can you guys see
Yes,
my?
yes.
All right. So this other equation here tells us what point the maximum or the minimum is on the x2 plane. All right. So let's find the differential. We'll first find this first differential, the theta dx1. All right. So first we'll be differentiating respect to x1. So by differentiating this equation here, okay. So if we're differentiating this equation with respect to one, we use quotient rule. So now, quotient rule, okay. I think we should still remember quotient rule. If you have a function like this, y equals to v over u. Sorry, u over v. Then we know that it's going to be equals to v squared over v du minus u dv. This is differentiating with respect to the particular variable we're talking about. So here we're talking about x1. So we're differentiating theta here, this theta, with respect to x1. Okay, this is our u. And this is our v, sorry. This is our v. And this is our u. So now, if we differentiate u with respect to x1, that means u is going to give us 0. Now, if u is giving us 0, it means automatically this whole term, okay, sorry, Control Z, back here. If you differentiate this one with respect to x1, differential of a constant is 0. So it means that du equals to 0. Now, if du is equals to 0, it means this term is 0. So 0 times v, it means this whole term goes to 0. We get. So it means we're left with only this. We're left with only these terms now. Okay, so let's now find dv dx1. Now to find dv dx1, coming back here, this is our v. So it means we are differentiating this one with respect to x1. Okay, let me open another tab. All right, so we're back here. So we're differentiating this one with respect to x1. Now if we're differentiating this with respect to x1, let me just write the equation again. I have a question, something like this: 1 plus x1, okay, minus squared plus 1 minus x2 plus 1. Now if you notice, if we differentiate this term, it doesn't contain x1, so differential of this term will give us 0. It doesn't contain x1. Now this also, if we differentiate this term, it's going to give us 0. So it means actually what we're going to be differentiating will just be this one here. We'll differentiate this. All right, so let's differentiate this now. Right now, so differentiating this one, for instance, if we're differentiating this, remember differentiation rule, chain rule, you differentiate, you first say let u be equals to 1 minus, for instance, let u be equals to this. Now if u is equals to this, by the time you differentiate du, you have minus 1 du dx, du dx1, you have minus 1. Now if we say that u is equals to this and we have this, now it means our function here is equals to u squared. Now what is the f du? The f du is equals to 2u. So by chain rule says that we multiply the f du times du dx1. So that if we're multiplying the f du times du dx1, we're going to have this. We're going to have the f dx1 which is equals to this times this, the f over du times du dx1. So if you look at it, it's almost like this cancels this. It's almost like this cancels this. So we're having this one here, which is on this side, and this one, which is on this side. All right. So what I'm just saying is that we're going to multiply these two functions. Sorry, these two values. So now multiplying these two values together, it means we're going to have, let me take it back. Okay. I hope you still remember the, okay, I still remember it, but I'll be saying it in case you've forgotten. All right. So it means df over dx1 is equals to minus 2u. Now this is our value of u. So we impute it here. So it means we're going to be getting minus 2, 1 minus x1. Okay. Now remember the first rule says that the differential of the function with respect to any of the variable. This is x1, for instance. So we're differentiating with respect to x1 here. So we said it has to be equal to 0. So if we equate this to be equal to 0, okay, let's remove this since we have solved this already. So equals to this. So if we equate this to be 0, it means that 1 minus x1 equals to 0. Because by the time we divide both sides by -2, we'll get 0. So definitely x is equals to 1. We get. So now the same way, likewise, we'll come here. We'll differentiate theta with respect to x2. When we differentiate theta with respect to x2, we're also going to get the same answer actually. So we're going to get our x.
I have a question, Bernard, if you can hear me.
Right, what's the question?
Are we not? Is it not the whole thing was supposed to equate to 0, or just that
It is the
1
differential
minus
of the
x?
function with respect to each of the variable equal to 0. The first
Yes.
differential.
You said theta is 1 over that whole denominator. Is it not that quotient rule that will equate to 0?
The quotient rule. Yeah, it's the quotient
Like,
rule. Did I skip something?
the
Okay,
whole
I've actually skipped something. Yeah, I skipped
yeah,
this
this
part, right?
v du over v squared.
Yes. No, what we solved was we found. Okay, let me take it back again. Okay, so what we're supposed to find, we found dv actually. We found dv to be minus 2 1 minus x1. Can you remember what we just solved? Sorry, dv. Can't remember what we solved
Yeah.
previously because this is v. The whole of this down is v. We differentiated with respect to x1, this variable here, and we found our answer to be this. Remember? Are we there?
Yeah.
We found our
Yeah,
answer
yeah,
to
yeah.
this one here, dv. So now we're supposed to come back to this equation. That was what I skipped. Yeah, thanks for reminding me. We're supposed to come back to this equation here and substitute it into this equation. We'll substitute it for this dv here. But remember, this one is already 0. So it means our new equation is going to be this. So it means we're going to be having, let me check it again. Okay. So it means our d theta over the x1 is now going to be equals to v squared. Previously, this whole thing is our v. So it means this whole thing will be v squared. We get, so over v squared. I don't just want to write the whole thing again, but I will explain because it's still going to still multiply both cross multiply and it will be 0. So that's why I don't bother writing it. Then this whole thing is v, right? So it means this whole thing here is v. So it means this whole thing squared. Now back to this formula, it says minus u dv. So now it will be this minus, what was our u? We came here. Our u is this numerator, right? So let's not confuse this u that I used here with the previous u that we're using. I could as well use, for instance, z here, so that it doesn't confuse the other one, this other u that we're using here. We get this u is for the quotient rule. So this u that we're using here is the numerator, and from here, the numerator here is 1. So going back here, minus u dv. So our u is what? 1. So that's minus 1. Then what is our dv? Our dv is minus 2, 1 minus x, minus 2, then 1 minus x, 1. You get,
Sure? You don't like their full names there. Where? In the email. No. Which? So I have to do for them. I didn't write the
I'm doing a Zoom
Sure?
call. I'm doing a Zoom call. All right, so let's continue. So over v squared. Now, remember we said the first differential has to be equal to 0. So if this differential equals to 0, by the time we multiply this one multiplies this one. Okay, let me not make it rough. All right, so this one multiplies this one. So it means that this whole thing here equals to 0. I think we get that part. Do you get?
Yes.
Yeah.
Yes.
All right. So this numerator now equals to 0. So it means 2, this times minus 1 times minus 2, that's 2. Then 1 minus x1 equals to 0. So definitely x1 is equals to 1. So that's how we found x1. Any questions?
No.
Any question? All right. So it's the same thing that applies to finding x2 also. From here, we differentiate theta with respect to x2. Now differentiating with respect to this x2 here. Okay, should use black. We differentiate with respect to this. Sorry, x2, not the whole of that. Okay. X2. Differentiate with respect to x2 here. And if we differentiate with respect to x2, we're going to get x2 to be equals to x2 is also going to be equals to 1. Just the same rule that I followed. Use quotient rule and differentiating it. All right. So now that is just telling us that our graph, if for instance we have a graph like this, if for instance we have a graph like this, x2, sorry, x1, we have a graph like this, x2, and this is our function, which is theta. So it's telling us that, let's assume we write our readings. Maybe here is 1, here is 2, here is 1, here is 2. So it's telling us that our maximum point is going to occur at when x is equals to 1 here, and when x2 is equals to 1. So our maximum point is going to be here. So it's going to be here, but it doesn't mean that it is at when theta is 0. Let's take note. I believe we can see the plane. Let's try to like this plane. We're saying that x2 and x1, when they are equal to 1, is where the function is either minimum or maximum. It's not telling us anything about what theta is. It's just telling us that it's at this point. So it can be anywhere on this line. When you are visualizing this theta, we get, so it's anywhere passing through this point. It's just telling us that it's passing through this point. So next thing is now for us to determine maybe it's maximum or minimum, since we have found the point it passes through on the x1 and x2 plane. So to find the type of graph is going to be either minimum or maximum, we have to find the second differential. That's the theta, d squared theta over the x1 squared, and also the squared theta over the x2 squared. So now this is what we're going to be solving next. So we'll solve this, we'll solve this one, because actually they'll give us the same answer. We'll solve this one, then the same steps is what you just follow to solve this one. All right, so let's solve this, the theta over the x1, to find maybe it's maximum or minimum.
Ben,
Yeah.
I need to create a new meeting. Seems we have less than 1 minute.
All right.